What lies beyond the furthest star we can perceive? It is a question that has haunted philosophers and astronomers for millennia, a query that echoes in the silent chambers of the human mind. We gaze into the velvet blackness of the night sky, a tapestry woven with 1,000,000,000,000 points of ancient light, and our intuition demands an answer. If the universe is everything that exists, a vast and expanding cosmic ocean, then what are the shores upon which its waves are breaking? What is the universe expanding into if, by its very definition, there is nothing outside of it? This question feels like a paradox, a riddle posed by reality itself. Our minds are conditioned by the world we inhabit. We understand expansion as a process of encroachment, an entity moving into a pre-existing, larger space. Think of a single drop of ink falling into a glass of clear water. The ink cloud blossoms, its tendrils reaching outwards, occupying the volume the water once held exclusively. The ink expands times into times the water, or imagine a balloon being filled with air. Its rubber skin stretches, pushing against the surrounding atmosphere. The balloon grows, its boundary moving into the room. This is the simple, tangible expansion we know. But when we apply this earthly logic to the cosmos, it shatters. The universe is not an object sitting inside a larger container. There is no empty room for it to fill. There is no pre-existing void waiting to be conquered. The very framework of the question, shaped by our limited experience, may be the greatest impediment to grasping the profound and beautiful truth. To unravel this cosmic enigma, we must discard our most basic assumptions. We must journey back to a time when the heavens were thought to be perfect and unchanging, and witness the intellectual revolutions that ripped that placid vision apart. Our quest is not to find an edge to existence, but to understand the very fabric of it. For most of human history, the cosmos was a place of serene permanence. The ancient Greeks, brilliant observers of the heavens, envisioned a geocentric system of crystalline spheres. The stars were fixed points of light embedded in a celestial dome, rotating with perfect, divine predictability around the Earth. This was a universe that was finite, enclosed, and eternal. Its structure was comforting, its boundaries known. Even after Copernicus and Galileo placed the sun at the center of our solar system, the broader conception of the stars remained one of an immutable backdrop, a grand, static theatre for our local planetary drama. Sir Isaac Newton, the architect of classical mechanics, extended this theatre to an infinite scale. His law of universal gravitation described a cosmos governed by precise mathematical rules, a majestic clockwork mechanism set in motion by a divine hand. Newton's universe was a boundless three-dimensional grid, an infinite and eternal expanse of absolute space. In this immense void, stars and planets pulled on each other across the emptiness. But this infinite, static model concealed a troubling paradox. If gravity was a universally attractive force, and the universe was filled with an infinite number of stars, why hadn't they all collapsed together into a single, monstrous clump? Newton himself was deeply troubled by this, suggesting that in an infinite space, the gravitational pulls from all directions would perfectly balance out. It was an elegant, but ultimately unstable, solution. A cosmic house of cards that would collapse if even one star was slightly displaced. For centuries, this vision of a placid, unending, and unchanging cosmos prevailed. It was the default assumption of all scientific thought. Then, at the dawn of the 20th century, a young patent clerk in Switzerland began to contemplate the nature of light, time, and gravity. Albert Einstein, with his theory of general relativity, did not just refine Newton's ideas, he obliterated the very foundations upon which they were built. In Einstein's revolutionary vision, space was not a passive, empty stage. It was a dynamic, flexible entity inextricably woven together with time into a four-dimensional continuum known as space-time. Mass and energy, he proposed, told space-time how to curve, and the curvature of space-time, in turn, told mass and energy how to move. This is what we perceive as gravity. It is not a mysterious force acting at a distance, but the natural motion of objects following the contours of a warped reality. But when Einstein applied his magnificent equations to the universe as a whole, they yielded a truly shocking prediction. They decreed that the universe could not be static. The immense gravitational pull of all the matter within it would inevitably cause the fabric of space-time to collapse in on itself. The universe, according to his own theory, should be contracting. This conclusion was so philosophically repugnant to Einstein, so at odds with the prevailing scientific consensus of a static cosmos, that he refused to accept it. He believed his own mathematics had revealed a flaw. To counteract this predicted collapse and enforce a state of cosmic stability, he introduced a fudge factor, an extra term into his elegant equations. He called it the cosmological constant. It was a hypothetical, repulsive energy inherent in the vacuum of space itself, a kind of anti-gravity perfectly calibrated to balance the pull of matter, holding the universe in a delicate, eternal equilibrium. Years later, Einstein would call this modification his greatest blunder. He had been standing at the precipice of one of the most profound discoveries in history, but had faltered, allowing his intuition to overrule his own revolutionary theory. The universe was not static, and the proof was being gathered, not by theorists in Germany, but by astronomers peering through giant telescopes in America. The story of this revelation begins not with a bang, but with a whisper of shifting light. In the early 1910s, an astronomer named Vesto Slipher at the Lowell Observatory in Arizona was performing a meticulous and arduous task. He was studying the light from faint, swirling celestial objects known as spiral nebulae. Using a spectroscope, he broke their faint light down into its constituent colors, creating a rainbow-like spectrum for each one. Imprinted on these spectra were dark lines, the unique chemical fingerprints of the elements within the nebulae. Slipher noticed something deeply strange. For nearly all of the nebulae he observed, these spectral lines were shifted. They were not where they were supposed to be. They had been systematically displaced towards the red end of the spectrum. This phenomenon, known as redshift, had a well-understood explanation. It was the cosmic equivalent of the Doppler effect, the change in pitch of a siren as an ambulance races past you. As the ambulance approaches, the sound waves are compressed, raising the pitch. As it speeds away, the sound waves are stretched, lowering the pitch. Light behaves in a similar way. If an object is moving toward us, its light waves are compressed, shifting them toward the blue end of the spectrum. If an object is moving away from us, its light waves are stretched, shifting them toward the red end of the spectrum. What Slipher was observing was staggering. The vast majority of these nebulae were not just moving, they were hurtling away from us at incredible velocities, some at over 1,000,000 miles per hour. The universe was not serene. It was a place of immense, directed motion. But the true scale of this motion remained unknown, because no one knew how far away these nebulae truly were. The key to unlocking cosmic distances came from the meticulous work of Henrietta Swan Leavitt, an astronomer at the Harvard College Observatory. Working as a human computer, she was tasked with cataloging the brightness of stars. She focused on a special class of pulsating stars called Cepheid variables. Leavitt discovered a remarkable, clockwork-like relationship. The brighter a Cepheid star was intrinsically, the longer it took to complete its cycle of pulsation. This was a discovery of monumental importance. It meant that Cepheid variables could be used as cosmic mile markers or standard candles. By observing the pulsation period of a distant Cepheid, astronomers could determine its true, intrinsic brightness. By comparing this to its apparent brightness as seen from Earth, they could calculate its distance with unprecedented accuracy. Leavitt had handed the world a celestial measuring tape. It was Edwin Hubble, a charismatic and ambitious astronomer using the new 100-inch Hooker telescope at Mount Wilson Observatory in California, who put all the pieces together. In the early 1920s, the prevailing view was that our Milky Way galaxy was the entirety of the universe, and that the spiral nebulae were simply gas clouds within it. Hubble aimed the world's most powerful telescope at the largest of these, the Andromeda Nebula. After painstaking observation, In 1923, he identified a Cepheid variable star within it. He used Leavitt's period-luminosity relationship to calculate its distance. The result was breathtaking. The Andromeda Nebula was not a cloud within our galaxy. It was nearly 1 million light-years away, a colossal, independent island of stars, a galaxy in its own right, comparable in size to our own. In that moment, the known universe expanded 100-fold. The sky was not filled with nearby clouds, but with countless other galaxies, each a sprawling metropolis of billions of stars. Hubble then combined his distance measurements with Slipher's redshift data. He plotted the distance to a galaxy against the speed at which it was receding from us. The result, published in 1929, was a straight line on a graph, a simple but profound relationship that would forever change our understanding of existence. This was Hubble's law. The farther away a galaxy is, the faster it is moving away from us. This was not random motion. It was not galaxies flying away from some central point in space. This was the signature of a uniform expansion, happening everywhere at once. The universe was getting bigger. Einstein's greatest blunder was, in fact, his theory's greatest prediction. The evidence was undeniable, but this discovery only deepened the central mystery. If everything is flying apart, what is it all flying apart times into asterisk? To grasp the answer, we must retrain our intuition. Let us perform a thought experiment. Imagine we are bakers, making a loaf of raisin bread. We mix the dough and stud it with raisins. We place the loaf in the oven and watch it rise. As the dough expands, every single raisin moves away from every other raisin. From the perspective of any individual raisin, it would appear that all the other raisins are receding from it. The more distant raisins, embedded in more intervening dough, would move away faster. This is a perfect analogy for Hubble's law. There is no center to the expansion. It is happening everywhere within the dough. Crucially, the raisins are not moving times through times the dough. The raisins are stationary, and the dough itself, the very space between them, is expanding, carrying them along for the ride. The loaf of bread is not expanding into a pre-existing emptiness in the oven. The substance of the loaf itself is stretching. In this analogy, we, our planet, our galaxy, are one of those raisins, and the expanding dough is the fabric of space-time. Galaxies are not projectiles hurtling through a static void. The very space between the galaxies is being created, stretching and expanding over time, pushing the galaxies further and further apart. The expansion of the universe is not an explosion in the conventional sense. An explosion has a center, a point of origin from which shrapnel flies outward into the surrounding air. The Big Bang was not an explosion times in time-space. It was the explosion times of time-space. It happened everywhere, at every point in the universe, simultaneously. Therefore, there is no center to the universe, and there is no edge. Asking what the universe is expanding into is a category error. It presumes an outside, a context that simply does not exist. Let's try another analogy to bend our minds around this concept. Imagine you are a two-dimensional creature, an ant, living on the surface of a vast, uninflated balloon. Your entire world, your entire reality, is the two-dimensional rubber skin of that balloon. You can move forward and backward, left and right, but the concept of up or down is meaningless to you. It is a third dimension you cannot perceive or interact with. Now, someone begins to inflate the balloon, where, as the rubber skin stretches, you, the ant, would observe something remarkable. Every other point on the balloon's surface would appear to be moving away from you. Points that were close by would recede slowly. Points on the far side of the balloon would recede much more quickly. This is a perfect two-dimensional representation of Hubble's law. From your perspective, it would look like you are at the center of this expansion, but another ant on a different part of the balloon would have the exact same impression. There is no center on the surface of the balloon. There is also no edge. You could walk forever in one direction and never fall off. You would simply end up back where you started. Your universe is finite, but it is unbounded. Now, if you were a particularly clever two-dimensional ant scientist, you might ask, What is my two-dimensional universe, expanding times into asterisk? The answer, of course, is the third dimension of the room in which the balloon sits. But for you, the ant, this third dimension is a fundamentally inaccessible, perhaps even unimaginable, reality. Our own three-dimensional universe might be behaving in a similar fashion. The expansion of our three dimensions of space could be happening within a higher dimensional reality, a hyperspace or bulk that we are incapable of perceiving. In this view, our universe is like a membrane, a brain, floating in a higher dimensional space. This is a compelling idea, explored by theories like string theory, but it remains highly speculative. The more standard, and perhaps more mind-bending, answer is that our universe does not require a higher dimension to expand into. The rules of geometry and space-time allow for the metric of space itself to stretch, without being embedded in anything else. It is a self-contained, self-expanding system. The geometry of space-time itself dictates the ultimate fate of our cosmos. According to Einstein's equations, there are three primary possibilities for the overall shape of the universe. It could be closed, like the surface of a four-dimensional sphere. In this model, the universe is finite in volume, but has no boundary. The combined gravity of all the matter and energy within it would be strong enough to eventually halt the expansion and reverse it, leading to a final, fiery collapse known as the Big Crunch. Parallel lines in a closed universe would eventually converge. Alternatively, the universe could be open, with a shape analogous to a four-dimensional saddle. This universe is infinite and unbounded. There isn't enough matter and gravity to stop the expansion, so it would continue to expand forever, though at a steadily decelerating rate. Parallel lines in an open universe would diverge. The third possibility is a flat universe. In this scenario, the universe is perfectly balanced on a knife's edge. It extends infinitely, and the expansion would slow down over time, approaching, but never quite reaching, a complete halt. In a flat universe, just as in the geometry we learned in school, parallel lines remain parallel forever. For decades, cosmologists debated which of these models described our reality. The fate of everything depended on a single number, the critical density of the universe. The race was on to measure all the matter and energy, to weigh the cosmos, and to determine our ultimate destiny. Then, in 1998, cosmology was thrown into turmoil by a discovery so unexpected, it felt like a violation of cosmic law. Two independent teams of astronomers were using distant supernovae, the spectacular explosions of dying stars, as new standard candles to measure the expansion rate of the universe. Deep in its past, they fully expected to find that the expansion was slowing down due to gravity's relentless pull. Instead, they found the exact opposite. The data clearly, unambiguously, showed that billions of years ago, the expansion was slower than it is today. The expansion of the universe is not decelerating, it is accelerating. Something is pushing space-time apart, overpowering the collective gravity of 1 trillion galaxies. This mysterious, anti-gravitational force was given a name: dark energy. We do not know what it is. It appears to be a property of the vacuum of space itself, an intrinsic energy of emptiness that exerts a negative, repulsive pressure. It is the modern incarnation of Einstein's cosmological constant, the fudge factor he invented to keep the universe static. But the universe is not static, and this energy is not a stabilizing force. It is a runaway engine, pushing the cosmos toward a strange and desolate future. This discovery profoundly changes our cosmic forecast. The Big Crunch is no longer a viable destiny. Instead, we face a far colder, lonelier fate. If dark energy remains constant, our universe is headed for a big freeze. As space continues to accelerate its expansion, galaxies will be pushed away from us at an ever-increasing rate. One by one, they will cross a cosmic event horizon, their light redshifted into oblivion, their presence erased from our sky. In 100 billion years, an observer in our own galaxy, by then a merger of the Milky Way and Andromeda, would look out into the night and see nothing but an endless, featureless void. All other galaxies will have receded beyond the reach of our most powerful telescopes, becoming causally disconnected from us forever. The universe will become a collection of isolated island galaxies in an ocean of accelerating blackness. Over trillions of years, the stars within those galaxies will burn out. The cosmos will grow dark and cold, populated only by black holes, neutron stars, and frozen cinders. An even more speculative and terrifying possibility is the Big Rip. If the repulsive force of dark energy grows stronger over time, it could eventually become powerful enough to overcome not just the gravity between galaxies, but all other fundamental forces. In the final moments of the universe, this phantom menace would first tear apart our galaxy. Then, it would rip solar systems apart, unbinding planets from their stars. In the last few minutes, Earth itself would be destroyed. In the final fraction of a second, atoms would be torn asunder, and space-time itself would be ripped into infinity. Every structure, on every scale, would be violently shredded. This bewildering discovery of dark energy adds another layer to our central question. The nothing of the vacuum is not truly nothing. It possesses a strange, inherent energy that is driving the very fate of existence. This forces us to re-examine the second part of our query. What do we even mean by nothing? In the realm of classical physics, nothing is simple, the absence of everything, an empty, inert void. But quantum mechanics, our theory of the very small, paints a dramatically different picture. The quantum vacuum is a seething, effervescent, and chaotic place. According to the uncertainty principle, energy can be borrowed from the vacuum for incredibly short periods of time. This borrowed energy can manifest as pairs of virtual particles and antiparticles which pop into existence from nothingness, exist for a fleeting moment, and then annihilate each other, returning their energy to the vacuum. The empty space all around us is, at its most fundamental level, a roiling foam of quantum activity. This is not just a theoretical fantasy. The existence of this quantum foam has been experimentally verified through a phenomenon known as the Casimir effect. If you place two uncharged parallel metal plates extremely close together in a vacuum, they will be pushed together by an invisible force. The reason is that the tiny space between the plates restricts the types of virtual particles that can pop into existence there. Fewer particles can form inside than outside. This creates a pressure differential as the greater storm of virtual particles in the outside vacuum pushes the plates together. Nothingness, it turns out, has substance and exerts real, measurable pressure. So, if the universe is expanding, it is stretching a vacuum that is already a dynamic and energetic entity. The nothing that space is being created from is, in fact, a something of profound complexity. So where does this leave us in our quest? We have journeyed from a fixed celestial sphere to an infinite clockwork machine, to a dynamic, curving space-time, to an accelerating, runaway cosmos. We have learned that the question, what is the universe expanding into, is likely a flawed one, born from a terrestrial intuition that fails at cosmic scales. The most widely accepted scientific answer is that it is not expanding times into times anything. The very fabric of space-time itself is stretching, creating more space as it goes. It is a self-contained system that needs no outside container. Like the surface of a sphere, it can be finite yet unbounded. Or like a flat plane, it can be infinite, with the expansion happening internally, everywhere at once. But science thrives on the frontier of what we do not know, and there are more exotic possibilities that directly address the question as it was asked. Theories of a multiverse suggest that our universe is not unique. Perhaps it is just one bubble nucleating and expanding in a vast metaspace, a bulk. In this scenario, our cosmos times is times, expanding into something a higher dimensional space that may be home to an infinite number of other bubble universes, each with its own physical laws, its own history, its own destiny. Here, the expansion of our space is like the inflation of one bubble in an endless sea of foam. Another mind-bending concept is the holographic principle, which suggests that all the information contained within our three-dimensional universe could be encoded on a two-dimensional surface at its boundary, like a cosmic hologram. This idea radically redefines our notions of space, location, and reality itself, further blurring the lines between inside and outside, and what it even means for something to have a boundary. Ultimately, the question forces us to confront the limits of human language and imagination. Our concepts of inside and outside, of before and after, are tools forged in a world of three dimensions and a linear flow of time. When we try to apply them to the origin and totality of space-time itself, they may simply break. The universe is not obligated to conform to our common sense. It is what it is, described by the language of mathematics, which often leads us to conclusions that are deeply counterintuitive, yet demonstrably true. We stand on a tiny, fragile planet, orbiting an average star in an unremarkable galaxy. For a brief moment in cosmic history, a species has evolved that can look out into the vastness and not just wonder, but begin to comprehend. We have deciphered the light from dying stars billions of light years away. We have read the echoes of the Big Bang itself in the cosmic microwave background. We have constructed a story of our cosmos, a 13.8 billion year epic of creation and evolution. And in that story, the greatest revelations have come not from confirming what we thought we knew, but from discovering that reality is far stranger, grander, and more magnificent than we could ever have imagined. The universe is expanding. Not into an empty void, but through the continuous unfolding of space and time itself. The mystery is not what lies beyond the edge, for there may be no edge to find. The true mystery is the boundless, accelerating, and deeply enigmatic nature of the fabric of reality. Our journey to understand it is not a journey to a destination. It is a journey of perpetually expanding horizons. And the further we see, the more we realize how much more there is to discover, hidden in the beautiful darkness between the stars.